This video is for educational and informational purposes only. It does not constitute financial, legal, or technical advice. Always do your own research and consult qualified professionals before acting on anything you learn here. Welcome to Street Smart Finance. Today, we embark on a deep dive into Ethereum, the world's programmable blockchain, and the technology that powers its vast, rapidly evolving ecosystem. Whether you're an aspiring decentralized app builder, a blockchain enthusiast, or simply curious about how Ethereum is reshaping finance, identity, governance, and beyond, this episode is your complete guide. By the end, you'll understand Ethereum's core architecture, consensus mechanisms, smart contract machinery, token standards, major sub-ecosystems like DeFi and NFTs, scaling strategies, governance frameworks, and where it all goes next. Let's get started. The birth of Ethereum and vision. Ethereum's story begins in late 2013, when then 19-year-old Vitalik Buterin published the Ethereum white paper, proposing a blockchain not just for peer-to-peer digital currency, but for arbitrary programmable logic. Bitcoin proved decentralized consensus works for money. Vitalik asked, what if we extend that consensus to any application? In July 2015, after a crowd sale that raised over 31,000 Bitcoin, the Ethereum mainnet, known as Frontier, went live. This marked the first time developers worldwide could deploy smart contracts, immutable code that executes exactly as written, automatically enforcing rules and financial flows without intermediaries. Ethereum's founding vision combined three pillars: Turing-complete computation, a universal virtual machine capable of running any algorithmic logic; decentralized consensus, permissionless, trustless agreement on state transitions; token issuance and standards, native asset Ether, plus an open framework for user-defined tokens. Together, these capabilities set the stage for decentralized finance, self-sovereign identity, governance DAOs, and a new paradigm for digital collaboration. Core architecture, layers of Ethereum. At its heart, Ethereum divides into distinct technological layers: network layer, peer-to-peer, P2P, networking. Every Ethereum node runs a client, Geth, Open Ethereum, Nethermind, BSU, connecting to hundreds of peers via DVP2P protocol. They gossip transactions, new blocks, and chain tips, ensuring all nodes share a single view of the blockchain. Consensus layer, proof of stake. Since the merge, validators stake 32 ETH to join the validator set. Every 12 seconds, a random validator proposes a block, and a committee of other validators votes to attest its validity. After sufficient attestations, the block is finalized, preventing reorgs beyond that point. Execution layer, Ethereum Virtual Machine, EVM. A stack-based, quasi-Turing complete bytecode interpreter that runs smart contract instructions. When a user sends a transaction, the EVM executes the contract code, updates storage, and charges gas for each computational step. Data availability and storage, world state, and Merkle tries. The EVM maintains a global world state. Account balances, contract storage, anchored in Merkle Patricia tries for cryptographic integrity. Full nodes store this state, while light clients verify proofs on demand. Application layer, smart contracts and dApps, user-facing decentralized applications from decentralized exchanges to NFT marketplaces, interact with the network via these contracts. Understanding these layers clarifies how Ethereum maintains decentralization, security, and programmability simultaneously. Consensus evolution from POW to POS. In its first 7 years, Ethereum used proof of work, POW, where miners competed to solve cryptographic puzzles, securing the network but consuming vast energy. In September 2022, Ethereum completed the merge, transitioning fully to proof of stake, POS. Why the merge? Energy efficiency. POS slashes Ethereum's energy consumption by over 99%. Security posture, staking aligns economic incentives. Slashable offenses deter attacks more definitively than POW. Scalability, preparedness. POS paves the way for sharding and rollups by decoupling execution from consensus. How POS works. Validators and staking. Anyone deposits 32 ETH into the deposit contract to become a validator. Validators propose and attest to blocks, epochs, and slots. Time divides into slots, approximately 12 seconds, and epochs, 32 slots. Each slot has one proposer and a committee for attestations. Finality gadget, Casper, FFG, hybrid mechanism providing checkpoint finality. Once 2/3 of validators attest an epoch, it's finalized and irreversible, barring a massive slash. Post-merge upgrades like Shanghai enable staked ETH withdrawals, while future milestones will unlock massive scaling improvements. The Ethereum Virtual Machine and smart contracts. The Ethereum Virtual Machine, or EVM, is the runtime environment for smart contracts. It's a sandboxed, isolated computational engine where each node executes contract bytecode deterministically, ensuring all honest nodes reach the same result. EVM basics. Accounts types: externally owned accounts, EOAs, controlled by private keys, hold ETH, and initiate transactions. Contract accounts deploy bytecode and storage, cannot initiate transactions directly, they respond to calls. Gas model: every operation ADD slowed create consumes a predefined gas amount. Gas limit per block caps total computational work, preserving network health. User specified gas price, GUE per gas unit, to incentivize validators to include transactions. Storage and memory. Memory: temporary byte array per transaction, cleared afterward. Storage: persistent key value store attached to each contract account. Reading and writing storage costs significant gas, reflecting its stateful permanence. Smart contract languages. Solidity: JavaScript inspired, most popular high-level language with features like inheritance, libraries, and interface detection. Viper: Pythonic design with a focus on simplicity and security, limiting complex features to reduce attack surface. Yule and Yule Plus, EVM IR, intermediate language for optimized low-level contract code and for emerging EWASM targets. Together, the EVM and these languages enable immutable, auditable, and programmable trust with wide real-world applications. Token standards: ERC20, ERC721, ERC1155, and beyond. A core innovation in Ethereum's early days was the ERC20 standard, enabling interoperable fungible tokens. Today, dozens of standards power a multi-trillion-dollar token ecosystem. ERC20 fungible tokens. Standard methods: total supply, balance of, transfer, approve, transfer from. Applications: stablecoins, USDC, DAI, governance tokens, UNI, COMP, reward points, synthetic assets. ERC 721 non-fungible tokens, NFTs. Unique identifiers: each token ID is unique. Metadata: URIS, point to off-chain content. Marketplaces: OpenSea, Rarible, Foundation, allow users to mint, buy, sell digital art, collectibles, game assets. ERC 1155 multi-token standard. Hybrid model: single contract manages both fungible and non-fungible items via token type IDs. Use cases: gaming assets, armors, weapons, in-game currency in a unified contract. Emerging standards and EIPS. ERC 4626, tokenized vault standard, standardizes yield-bearing vault wrappers. ERC 4337, account abstraction. Smart contract wallets that treat EOAs and contracts uniformly, enabling social recovery and pay gas abstractions. Token standards drive seamless composability. Any ERC20 token can plug into DeFi protocols. Any ERC 721 can integrate with marketplaces or metaverse worlds. This modularity defines Ethereum's composable money Lego culture. DeFi, decentralized finance. Decentralized finance, DeFi, remains Ethereum's killer app. Starting with Uniswap in 2018, DeFi protocols unlock permissionless automated financial services. Core DeFi building blocks. Automated market makers, AMMS, Uniswap/SushiSwap, liquidity pools replace order books, traders swap tokens by paying a pool fee, and liquidity providers earn fees proportional to their share. Lending and borrowing, Avi, Compound, users deposit assets to earn interest or borrow against collateral. Over collateralization and adjustable interest rate models maintain solvency. Stablecoins, DAI, algorithmic over collateralized stablecoin via maker DAOs vaults. USDC, USDT, centralized issuers pegged 1-to-1 to USD reserves. Yield aggregators and vaults, Yearn Finance, auto compounds interest by migrating funds across protocols to chase highest yields. Derivatives and synthetic assets. Synthetics mint synthetic exposure to stocks, commodities, forex by staking SNX collateral. DeFi's impact. Over $80 billion in total value locked at peaks. Unlock credit markets to anyone worldwide. Permissionless innovation, novel risk models, flash loans, collateral swaps, risks, smart contract bugs, oracle manipulation, governance attacks, security audits and insurance protocols, Nexus Mutual, mitigate but don't eliminate risk. DeFi showcases Ethereum's unparalleled financial composability, but also highlights the need for continual security and user education efforts. NFTs, metaverse, and beyond. Non-fungible tokens, NFTs, expanded Ethereum's scope into art, gaming, identity, and metaverse ecosystems. NFT use cases, digital art and collectibles, CryptoPunks, Bored Ape Yacht Club, cultural phenomena driving creator royalties and provenance, gaming and virtual goods, Axie Infinity, Decentraland, players own in-game land, avatars, and items that can be traded cross-platform. Social fi and profile NFTs, ENS domains, soul-bound tokens to bind reputation or credentials to a wallet. Technical innovations. On-chain metadata and SVG art. Some projects store art entirely on-chain for censorship resistance. Layer 2 NFT marketplaces, Immutable X, Zora, offer faster, cheaper minting and trading while inheriting Ethereum's security. NFTs demonstrate the blockchain's potential as a universal ownership layer, melding art, community, and digital rights in programmable tokens. Scaling Ethereum, Layer 2s, and sharding. Ethereum's success brings congestion and high fees. Scaling requires a multi-pronged approach. Layer 2 rollups. Optimistic rollups. Optimism Arbitrum. Batch transactions off-chain, post-compressed data to L1. Fraud proofs allow anyone to challenge incorrect state transitions within a dispute window. Zero-knowledge rollups, ZK Sync, Starknet, generate succinct validity proofs for off-chain batches. L1 verifies the proof instantly, requiring no challenge window. Rollups inherit L1's security while offering 10 to 100 times throughput improvements and dramatically lower gas costs. Ethereum sharding, proto-dank sharding, and beyond. Data sharding splits data availability across 64 shards, increasing the amount of data Ethereum can process per block. Dank sharding and EIP 4844 blob transactions introduce cheap blobs for rollup data, reducing costs by an order of magnitude and accelerating rollup adoption. The synergy of POS consensus, data sharding, and rollups forms Ethereum's roadmap to thousands of transactions per second at L2, with L1 securing finality. Security, audits, and best practices. While decentralized, Ethereum protocols demand rigorous security to protect user funds and network integrity. Common vulnerabilities. Reentrancy attacks. Unchecked external calls can re-enter a contract before state updates, draining funds, e.g. DAO hack. Oracle manipulation. Flash loan price attacks on-chain oracles can skew protocol logic errors and overflows. Unhandled integer overflows, unchecked return values, or flawed access controls. Mitigation strategies. Formal audits. Firms like OpenZeppelin, Consen, SysDiligence, Trail of Bits examine code for vulnerabilities and suggest fixes. Bug bounty programs. Protocols incentivize white hat hackers to find bugs before exploitation. Upgradable contracts and governance pauses. Proxy patterns allow safe upgrades, while time lock mechanisms enable community review before critical changes. Security remains an ongoing arms race. Strong practices, user education, and decentralized guardrails help safeguard the ecosystem. Governance and protocol evolution. Ethereum evolves through community-driven Ethereum improvement proposals, EIPs. Anyone can propose changes, ranging from gas cost tweaks to consensus adjustments. EIP process. Draft initial idea published as EIP in text form on GitHub. Review and discussion. Community and core developers debate merits, trade-offs, and implementation details. Testnets and specifications. Code implementations on Goerli or Sepolia ensure stability. Core dev consensus. Core developers meet monthly to decide staging and future network upgrades. Mainnet deployment. Changes activate at pre-announced block numbers via hard forks, e.g. London, Shanghai. Major EIPs like EIP-1559, base fee burns, and EIP-4844, proto-dank sharding, reshape fees and scaling. This open, iterative governance model balances decentralization with pragmatic upgrades. Developer tooling and ecosystem. Ethereum's developer ecosystem flourishes with specialized tools, Remix IDE, in-browser code editor for rapid prototyping and debugging, Hardhat and Truffle, local development environments with compiling, testing, and scripting tasks, OpenZeppelin contracts, battle-tested libraries for common smart contract patterns, Infura and Alchemy, managed node infrastructure providing high availability JSON RPC endpoints, the Graph, indexing and querying blockchain data with GraphQL subgraphs. These tools slash development time, standardize best practices, and accelerate project launches across finance, gaming, identity, and beyond. The road ahead and future innovations. Ethereum's momentum shows no signs of slowing. Key future trends include full sharding rollout, enabling massive data capacity on L1, unlocking direct L2 competition, cross-chain interoperability, bridges like Layer 0 and Wormhole link Ethereum to other blockchains, creating a cohesive multi-chain future, account abstraction and smart accounts, ERC4337 wallets with built-in social recovery, sponsor-paid gas, and programmable security rules, decentralized identity, DID, and verifiable credentials, Ceramic ENS and ERC 725/735 standards for portable self-sovereign identity, on-chain governance and DAOs, liquid democracy experiments, quadratic voting schemes, and meta-governance layers for protocol decisions, Web3 data privacy and zero knowledge, ZK snarks and ZK starks powering private transactions, private DeFi, and confidential identity proofs. Ethereum remains the world's most active developer community with over 500 million transactions per year and thousands of dApps in production. Its open source permissionless ethos catalyzes innovation at a pace few platforms can match. Today we covered Ethereum's origins, layered architecture, POS consensus, EVM mechanics, token standards, DeFi, NFTs, scaling solutions, security best practices, governance processes, developer tools, and the exciting road ahead. Ethereum isn't just a blockchain, it's a global, decentralized computer powering the next generation of finance, art, governance, and identity. If you found this deep dive valuable, hit like, share with your network, and subscribe for more Street Smart Finance explorations. Drop your questions in the comments. What Ethereum topics should we cover next? Until next time, keep staking and keep building.